Welcome to this explainer. Today, we're completely bypassing the usual narratives of luxury to execute a strict methodological analysis of one of the most formidable private vessels ever constructed, Project Eclipse. Spanning a massive 162.5-meter profile, this is absolutely not your standard luxury review. We are undertaking a highly technical naval analysis of a marine structure that essentially blurs the line between a civilian mega-yacht and a sovereign defense frigate. The sheer density of systems integrated into this hull requires a strictly data-driven approach. To process this immense complexity, we'll break our analysis down into 5 sectors. 1. Structural parameters and valuation. 2. Tactical defense. 3. Subsurface evacuation. 4. Optical counterintelligence. And 5. Modular architectural engineering. Let's dive right in. Starting with Section 1, Structural parameters and valuation. Let's isolate the baseline metrics. The core financial metric here is an estimated current valuation of $1.5 billion. Now, you have to understand, this figure isn't just a product of premium materials. This valuation is directly driven by the integration of military-grade subsystems, unprecedented custom engineering solutions, and macroeconomic inflation over its operational lifespan. We're talking about a capital investment that literally mirrors national defense budgets. Constructed by German shipbuilder Blohm plus Voss and delivered in 2010, the Eclipse spans an immense 162.5 meters. To contextualize that dimensional data for a moment, that is equivalent to 1.5 professional football fields of highly specialized floating infrastructure. Its capacity supports 36 guests, maintained by a massive operational crew ranging from 66 to 70 personnel. Looking internally, that operational payload distribution is highly anomalous. We have a maximum crew of 70 personnel supporting just 36 guests. In naval engineering, a ratio this dense, nearly 2 crew members for every single guest, indicates an exceptionally complex network of subsystems. The sheer volume of mechanical, tactical, and hospitality protocols practically demands the specialized human workforce just to maintain systemic equilibrium. Tracking the chronological cost evolution provides some critical context here. The initial base construction required a $500 million investment, but interestingly, this base cost effectively tripled over its lifespan. This exponential financial delta was primarily generated by the implementation of military-grade integrations and custom mechanical engineering. And those are the exact technological upgrades we are going to methodically deconstruct right now. Moving to Section 2, Tactical Defense and Ballistics. We'll be evaluating structural superstructure enhancements and countermeasures. At the absolute core of its tactical framework is the implementation of a radar-guided defense shield. Functionally, this operates parallel to the defense grids utilized by sovereign warships. It relies on an omnidirectional threat detection matrix. So if an anomaly is detected, the system is theoretically capable of neutralizing incoming aerial threats alongside surface-level maritime threat engagement. Putting a missile defense system on a civilian hull is, frankly, an extreme divergence from standard maritime architecture. Just to really emphasize this divergence, a standard luxury yacht utilizes tempered marine glass and conventional fiberglass or steel hulls. The Eclipse, conversely, encloses its master suite and the captain's bridge within centimeter-thick bulletproof ballistic glass and rocket-proof steel armor plating. This kinetic mitigation architecture is engineered to withstand direct, high-velocity ballistic impacts, ensuring absolute command center integrity during hostile engagements. Next up, Section 3, Subsurface Evacuation Systems. Let's examine the lower hull tactical evasion protocols. The vessel's primary failsafe follows a strict algorithmic logic protocol. Let's say we're looking at a hostile boarding scenario, like piracy or a targeted terror attack. The structural engineering of the hull initiates the activation of a concealed moonpool bay. This controlled opening right in the base of the hull facilitates the rapid deployment of a specialized 3-person multi-environment submersible. The key metric for this extraction system is its 50-meter maximum operating depth. Tactically speaking, this deep-water protocol is absolutely vital. Plunging to 50 meters ensures complete evasion from surface-level radar arrays and visual detection. It's essentially a silent extraction mechanism that mathematically removes the primary targets from the hostile vector entirely. Section 4, Optical Counterintelligence. We're heading back up to the upper deck to look at electronic warfare systems. Now, popular media often refers to this as an anti-paparazzi shield, but in strict engineering terms, it's an automated infrared optical disruption system. This is a targeted electronic countermeasure designed solely to disrupt the optical sensors of digital cameras. By neutralizing unauthorized photography, the vessel actively manages its own visual footprint, maintaining rigorous operational security at all times. The disruption system executes a precise four-step algorithmic sequence. First, the hardware conducts continuous 360-degree infrared scanning of the environment. Second, the software utilizes automated signature detection to locate the specific reflection of a camera lens. Third, upon target lock, the system triggers a precision-directed photonic beam emission. And finally, this concentrated burst overexposes the target sensor, resulting in instantaneous data corruption. It effectively functions as a localized optical firewall. Finally, Section 5, Modular Architectural Engineering. Let's analyze the convertible maximum capacity payload topographies. Beyond defense systems, massive structural volume is dedicated to high-capacity payload spaces. The vessel is engineered with dual helipads in both forward and aft configurations, allowing for simultaneous aerial logistics. Internal bays house 3 rapid deployment speedboats, multiple integrated jet skis, and an entire beach club sector. The logistical footprint required to maintain and deploy these secondary vehicles demands incredibly robust, heavy-duty hydraulic systems. Perhaps the most profound example of this modular engineering is a single space supporting 2 completely distinct physical states. In Configuration A, it functions as a 16-meter structural swimming pool supporting high-volume fluid dynamic loading. However, through a complex hydraulic lift network, the water can be rapidly drained in the base mechanically elevated. Literally within seconds, the system shifts to Configuration B, forming a solid-state structural dry surface. This ability to physically alter architectural topography on demand is just an absolute masterpiece of fluid dynamics and mechanical engineering. Which brings us to our final analysis, evaluating this anomaly in civilian marine architecture. Synthesizing all this schematic data leaves us with a critical theoretical question. Is this level of militarization in naval engineering a new standard for the private sector, or is it merely an extreme anomaly? As wealth concentrates and security paradigms shift globally, are we going to see more civilian vessels adopting sovereign defense protocols? Take a look at the data we've presented, consider the current trajectory of marine architecture, and let us know your technical assessments in the comments below. Thank you for joining this explainer.